so just for your amusement, I'm going to start off with something. So today we're going to be talking about something called Arclength. Okay, Arclength. So you have some curve, and you'd like to figure out how long it is. Okay. So just for your amusement, I'm going to start off with something called the Koch Snowflake. Okay, and the way you make a Koch Snowflake is as follows. You start off with a line. Okay, let's say this line is of length 1. Okay. The line is of length 1, and then you so that's like the first step, and then you take that line and you erase the middle third of it. Okay, you erase the middle third of it, and you replace that with 2 copies of that middle third. Okay. So you take off this middle third, or rather you take that middle third and you angle it up, and then you take another copy of it and put it here. Okay. So that's step 2. And then step 3, you do the same thing for each interval. Everything that we did to this one long interval, we're going to do to each of these intervals. So you take this thing here, you take the first interval, you erase its first third, you erase all the thirds, all the middle thirds of these intervals, and you replace them with these spikes. Okay, right, and then you do the same thing. So that's step 3. Step 4, you do the same thing. You take the previous guy, and you erase all the middle thirds of that guy. Right, all the middle thirds of that guy, and then you put these little spikes on them. Okay, and then you keep on going. Okay, and the thing that you get as time goes to infinity is called the Koch Snowflake. Or actually, I think normally you start off with a triangle, and then you put the bumps on each side, and it starts to look more and more like a snowflake. Okay, so this is just part of it. But anyway, we'll say that this is the Koch Snowflake. Okay, so how long? So this thing at the end is called the Koch Snowflake. I'd like to know how long is the Koch Snowflake? How long is the Koch Snowflake? Well, let's think. Well, this thing was length 1, right? Right. Well, how long is this?
1 1/3.
Yeah, it's 4 thirds, right? 1 1/3. Right. Well, how long is this then? 16 ninths, right? You've taken everything, you've multiplied every length by 4 thirds again. Right here you took a length and you basically increased it by multiplied it by 4 thirds. Here you've taken each part of it and you've increased that length by 4 thirds. Right, so you multiply it by 4 thirds again. So, right, so this length is 4 thirds, this length is 4 thirds squared, and so on and so forth. Right? And so you see that as time goes on, you get something of maybe should be called having infinite length, right? Because 4 thirds times itself infinitely many times tends towards infinity. Okay, so this is an example of something that's called a fractal. A fractal object. Fractal is an abbreviation for something of a fractional dimension, I think. Something of fractional dimension. So these things are considered to be something more than one-dimensional and something less than two-dimensional. Yeah. This is related to the question of how do you measure the length of a coastline, right? How do you measure the length of a coastline? So you've got your coast. Right, I don't know what country this is. You've got some coast here, right, and you want to measure the coastline. Well, it's actually impossible to get the length of a coastline because it really depends on how long your ruler is, right? if my ruler is suppose I have a foot-long ruler, and I say, oh, how long is this thing? Well, it looks like it's about 1 foot long, right? But if I take a smaller ruler, maybe along, a smaller ruler, oh look, actually this thing is more. I can catch more of the detail, right? And I see that this thing is actually longer. And it turns out that the smaller ruler that you take, the longer your coastline will get, right? So it's actually pretty hard to determine the length of the coastline. Okay. Anyway, so this is just starting us, try to get us into the idea of Arclength. So we will not deal with things of fractional dimension or anything like that. We will, if we did, we'd be in trouble, right? Because we'd have to. It would be difficult to do. So we'll consider only smooth functions. Smooth functions. Okay, you see that these things are very not smooth, they're very bumpy, right? We'll consider only smooth functions, so that is to say, you have some function on an interval, and f prime is continuous. Okay, so this is what we're going to use as smooth. Okay, it's not going to be. This is what we'll mean by smooth. That it has a first derivative, and the first derivative is continuous. Okay, and so. Okay, so we'll have the graph of that function, right? The graph of that function, y equals f of x, right? And we'd like to know what is the length. Okay, what is the length? Okay, so again, calculus is sort of, you go back to elementary school, and so you go to an elementary school student, and you say, what is the length of this? What is the length of this curvy thing, right? And you in elementary school would say, I have no idea, right? I have no idea. I know how to get the length between 2 points, right? I know how to get the length between 2 points, but I have no idea how to get the length of this curvy thing. Okay. So I know I've sort of said this before, but the motto of calculus is there's basically one idea in calculus, and it's this, that the unknown can be studied as the limit of the known. The unknown can be studied as the limit of the known. Okay. So you take your elementary school knowledge, which is how to get the distance between 2 points, and say, okay, I don't know how to do this, but I do know how to do this. Okay, right? I do know how to do this. So you say, okay, I can do that, and I could get the length of this thing. Right, and I could take, so you chop your base into, a certain number of parts. I can get the length of that thing. You chop your base into more parts, right? You say, oh well, as an elementary school student, I have the ability to get the length of that thing, right? Because I know how to get the distance between 2 points, and I know how to add. Okay. And then we combine that with the one big tool of calculus, which is the limit, right? We'll take the limit of that, and that's going to be our arc length. Okay, so that's what we're going to do. Let's see what we get. Okay, so let's draw a picture again. A, B, right? So you have some axis. You have some axis here. We're going to chop this thing up into n parts, right? So let's call them x0, x1, x2, xn, xn minus 1. Okay. Okay, and let's then take these points above, take these points here, and write down an expression for the length. The length of the piecewise linear curve, piecewise linear approximation is, so we create something that is not linear, but its pieces are linear, right? And then we write down some approximation, we write down some expression for that length. Okay. Take a minute and see if you can write something down. Okay. If these points are x0, x1, x2, blah, 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 and this is the graph of your function f of x, then what's the length at the nth stage, right? At the nth stage, the length will be something. Okay, so see if you can write something down. It might be helpful to start off with just a 2, right? x0, x1, x2, right? And write down what that expression would be, and then just extend it afterwards. Okay, turn to somebody nearby, talk with them. Snowy will talk with you this week. You talk with us. Yeah.
Could you take a So like if you have the curve, you have 2 points, you could take area delta. This would be the square root of changing that, changing x.
Okay, would somebody like to tell me either the full-blown thing or the sort of initial part? Okay, Hannah, which one do you want to do?
Of the
This one? This one?
anything.
Anyone? Okay. Let's do this one. Let's say this is the easy one, the first one.
Do the fx1
fx1. So
minus fx naught, and you square it. You use the distance formula, like the square it
okay.
plus parenthesis x1 minus x naught, square it, and then root that square root.
Square it.
And then do the same
Right. Okay, and then do the, so let me say it again. I'll write it again. This point is x naught, f of x naught. Right, this point is x1, f of x1. This point is x2, f of x2. Right? So you just use the distance formula on each pair. Right? You say, well, the distance between the first two guys, so the distance between the first two guys is going to be, x1 minus x naught squared plus f of x1 minus f of x naught squared, right? That's this distance, right, by the Pythagorean theorem. Everybody okay with that? Okay, right. And then you do the same thing for the second pair, right? x2 minus x1 squared plus f of x2 minus f of x1 squared, right? And that would be this length. Okay. Any questions? Okay, right. And here you just have the same thing, but we have endpoints rather than just 2 points. So for this guy, we're going to write it as the sum as k goes from 1 to n of the square root of xk minus 1 squared plus f of xk minus f of xk minus 1 squared. Right. So this is the length. This is the length at the nth stage. Right. Right. You're going to let your index goes from from 1 to n. Right. You take each point minus the x. You take the difference between that point and the distance between that point and the previous point. Okay. Right. Anybody confused? Anybody confused? Close your eyes, please. Close your eyes. Raise a finger if you're confused. Okay, open your eyes. Thank you. Okay. It's interesting because before you close your eyes, I was for sure that somebody was confused, but actually you're all fine. Good. Yeah. You're still writing it down?
Yeah.
It's the same thing as this.
Oh,
it's the same thing as this. Okay. Like faster. Okay. So this is the nth. This is what you have at the nth stage, right? And then so you take the limit of that, right? Take the limit of that, and the limit is going to be what we call the arc length. Okay. So so take the limit of that. So arc length. So let's take the limit. Take the limit as n goes to infinity. Right? As n goes to infinity. Okay. So let me change the notation a little bit. So let's say it like this. So before we take the limit, let me change the notation slightly. Let's let delta x let delta x be b minus a over n. Okay, it's just the width of one of these subintervals. Okay, delta x. Okay, so for example, this thing here is delta x, right? Xk minus 1. That's delta x. right? So now I'm going to rewrite this. Rewrite the above as follows. We'll do it in kind of a funny way. I'll rewrite it like this. Sum from k from 1 to n, the square root of delta x squared plus f xk minus f xk minus 1 quantity squared. Okay, I'm going to do something funny. I'm going to multiply by delta x, and I'm going to divide by delta x. Okay. Well, that's the same thing as if I can put this guy on the bottom, I can write as the square root of delta x squared. Right? This delta x on the bottom, I just write as the square root of delta x squared. Right? And the square root, if you take a quotient of square roots, it's the square root of the quotient. So I'm going to combine those together. Right? I'll say it's just the square root of delta x squared plus this guy everything over delta x squared. Delta x on the outside. Okay, so that's the same thing as the square root of, if I break this thing, sorry, hold on. We're talking. Okay, well, I'm going to break this into this fraction into two parts. Okay, it'll be 1 plus this thing over this thing squared dx. Right? So I switch this back into this form. It's the same thing, of course. Okay. Everybody all right? Everybody all right? Any questions? Any questions? Okay. So this is how I want to write the length at the nth stage. And now let's let n go to infinity. This is the length at the nth stage. So now let n go to infinity. And what do you see? What's going to happen? What's going to happen? As n goes to infinity, you've got this f of xk minus f of x k minus 1 over this thing. Well, what is this? Does anybody recognize this? This should look kind of familiar, right? What's going to happen? What's going to happen? You've got this xk minus 1, right? You've got f of xk minus f of xk minus 1 over xk minus xk minus 1, and they're going to get infinitely close to each other. And
it's the slope, right?
It's the slope, right? It's the slope. But when you let these guys become infinitely close, what are you going to get? There. It's the derivative, right? So you're going to get the derivative at some point, right? Okay, right. So what you see is that this thing is the Riemann sum is a Riemann sum for a certain integral. Right? What's the integral? Well, the integral from a to b of the square root of 1 plus f prime x dx. Squared, excuse me, squared. Thank you. Squared. Okay. And so this is the part that the elementary school student wouldn't get. Okay. But once that student got to college, he'd say, well, look, you can take that thing that you figured out in elementary school and take the limit of it, and it turns into this integral, and this is what we're going to call the arc length. Okay. So this is the expression we use for the arc length. Arc length is the arc length of the graph of f of x over the interval a comma b. Okay, does that make sense? Everybody okay? Okay, so you take your simple expression that's just talking about a sum of distances, and then you let over a certain partition, and then you let that partition become infinitely fine, let n go to infinity, and you say, oh look, well this is just the Riemann sum that, and as n goes to infinity, it'll turn into this integral. Okay, so that's the integral. So, for example, if somebody gave you a function f of x being x cubed over 3 plus 1/4 x, 1 over 4x, excuse me, over the interval 1 comma 3, then what would be the arc length? What would be the arc length? Take 1 minute and write down the expression and we don't evaluate it. I think evaluating will be a little tricky, but at least write down the form, what the formula gives you. Let's just write this down. So, what's S prime? What's F prime? Is it too easy? x squared? Yep.
Minus 4 over 16 x squared.
Minus, what's that?
16.
4.
4 over 16 x
4 over 16. It's just 1/4, I think, right? You've got 1/4 x to the negative 1. You differentiate it, right? You get, when you differentiate that, you get negative 1/4 x to the negative 2. Right? So negative 1/4. Oh, I see. You squared it. You squared it already. Yeah, I see. So yeah. So then you would square that. Right? You would get x to the 4th minus a half, right? Plus 1/16 at x to the negative 4th. Right? And so the arc length would be the integral from 1 to 3 of the square root of 1 plus that. Right? So x to the 4th plus a half plus the 16th x to the negative 4th. Okay. Let me put up one that's maybe more tractable. F of x is the integral from 0 to x of the square root of secant to the 4th x minus 1. Sorry, t dt. Okay. So again, this one between negative pi over 4 and pi over 4. Okay. So take a minute and just write down what the formula would be. Okay, turn to somebody nearby and talk with them, please.
Oh, right.
Okay, so what's the derivative of this? What's the derivative of this? Mira, how about you?
I'm kind of uncertain right now.
Okay, so remember the fundamental theorem of calculus says if you have something like this and then you differentiate it with respect to, if you have some sort of integral from 0 to a variable and you differentiate that thing with respect to the variable, you're going to get the integrand back. So this is exactly that sort of thing, right? So when we differentiate this, we're going to end up with just the integrand. Right? We just end up with the integrand by the fundamental theorem of calculus. Okay, so then, the square, of course, is just going to be secant to the 4th minus 1, right? And then the arc length is going to be Somebody, how about Anna? You tell me?
So the Arclength would be the integral from negative pi over 4 to pi over 4 of the square root of 1 plus the square root of secant to the fourth x minus 1 squared.
Yeah, so which would just be the secant to the fourth minus 1. So those ones cancel off, right? And then you would get the square root of the secant to the fourth, which turns out to be the secant squared in this range, because the cosine is going to be positive there, right? And so, that turns out to be tangent of pi over 4 minus tangent of negative pi over 4, which is to say 2. Yes, Julie?
Wait, why did you put x here instead of 1?
I crossed off the 1 and the negative 1.
Okay,
Yeah.
sorry.
It's not an x. Yeah, I'm sorry. It looks exactly like an x. Sorry. Yes, Hannah?
You're not square root the square derivative.
So you take the derivative, this was the derivative, it had a square root on it. When I squared it, then the square root vanished. Okay. So I hope you're getting a sense of how to do the arc length, right? It's pretty straightforward. You just have this formula. So that's the arc length of a graph, right? We're going to do something a little bit different. Arc length of a parameterized curve. Arc length of a parameterized curve. Okay, so that is, you have a curve, gamma of t being like x of t, y of t. Okay, so for example, you could have something like gamma of t is cosine t, sine t, as t ranges from 0 to 2 pi. Right? So, does anybody know what this looks like? What this looks like? Cosine t sine t as t ranges from 0 to 2 pi. Well, at 0, you're going to get cosine 0 sine 0. What's that? Joanna, you're drawing it?
It's a circle.
It's a circle, right? This is the parameterization of the circle. Right? At time 0, you're here. As the t increases, your angle increases, and you just walk around the unit circle until you come back to 2 pi. Okay, so this is a parameterization of the unit circle. Okay. So you could have something crazier than that, right? You could have this basically just describes a point walking around in space, right? A point walking around in the plane. So this allows us to do something better than just a graph, right? We can do something better. Okay. And so again, you go back to elementary school and bother the children there. And you say, well, kid, how about, how would you get the length of this? And they say, well, I don't know how to get the length of that. I told you before, I don't know how to get the length of these sorts of things. But, we do know how to chop this thing up into pieces, right? And then take the lengths of those guys. Okay. So, what you would get, what they would do basically is they would take the time period, right? Here's your time going from A to B, right? And they would chop that time up into parts, right? So T naught, T1, T2, through Tn, right? And then say, okay, Well, I'm just going to take these points. This guy is x of t0, y of t0. This guy is x of t1, y of t1. And then although I don't know the answer to your question, I do know how to get the distance between these 2 points. Right? It's going to be x minus x1. This is x minus that x squared. This y minus that y squared. Right? And run through the same thing. Right? So the nth, as before, the nth approximation will be summation x tk minus x tk minus 1 squared plus y tk minus y tk minus 1 squared. Everything square rooted as k goes from 1 to n. Elizabeth, you signed. Why are you signed?
Just a lot to write down.
It's a lot to write down, but it's simple to see, to understand, right? This is the distance between those 2 points, right? It's the sum of distances, right? This distance plus that distance plus that distance, right? So this thing here is the distance from one point, the kth point to the k minus 1 point. Right? And you take the sum as k goes from 1 to n. Okay. We play exactly the same game as before. We're going to divide by delta t, multiply by delta t, right? And then take the limit as n goes to infinity, and we get an integral. The integral will be, well, see if you can write it down. What will the integral be? Okay, I'll give 1 point on the next exam to the person who tells me first. Kara, you're smiling? No. Okay. Anybody want to try? Kate?
Isn't it just the same as before?
Close.
So like 1 plus f prime?
No. No.
No.
No. Not exactly. Not exactly. So this t is going to be, your t sub k minus t sub k minus 1. When we put it in, it becomes squared, right? And then we'll get the square root of this thing squared plus this thing squared, this quotient squared, right? As n goes to infinity, this thing is going to turn into Chandler? The derivative of what?
All of that gibberish squared.
If you say gibberish, I'm not going to give you any points. Mary? Mary, big point.
The derivative.
Minus 1 point on you. What?
The derivative of the x function?
Yes, exactly. The derivative of the x function. So not gibberish. My God. Okay, you get the derivative of x plus the derivative of y dt. Right? Integrated between a and b. Right? If you say gibberish, that sort of tells me that you don't know. You don't know. It should be something simple. Okay. So, so just quickly, if we wanted this thing here to find the arc length, you know what it is, but suppose we wanted it. Well, we get the integral from 0 to 2 pi of the square root of the x prime squared plus y prime squared. Right? X of t is cosine t, y of t is sine of t. Right? So we would get x prime squared plus y prime squared dt, right? But that's the integral of 1. Right? And so you get 2 pi. Okay, Chandler, you actually don't get -1 points. Okay, that's it for today.